All right, so we can. Okay, so let me share the screen. Okay, so, let's get started. So today in the lecture, we're going to continue the last lecture, which was the introduction to PyTorch. You remember, so we're going to continue our sequence of neural nets. So today we're going to continue, right, with our first PyTorch script for the iris dataset, right? And then we're going to go over some additional background examples and also explore the XOR problem. So those are two very classic data sets or problems that we're going to look at, and they give us a lot of information about neural networks in general, okay? Also, I'll remind you that the presentations are going to continue this Thursday for those of you that haven't, not everyone has presented, right? So we only have time for like the KNN, yes, the KNN averaging thing. So that's, you can present that this Thursday. For those of you that already presented, I posted the grade if you've submitted your report. If you haven't submitted your report, I still haven't issued your grade. So please don't forget to submit that, okay? And of course, you need to present to get a grade. All right, so yeah, so that's the plan. So today we're done with the KNN averaging. That was one algorithm, just kind of cover the whole pipeline basically. And now we're in like the second third of this class, which is PyTorch basically. This sequence will end in the SciFAR 10 contest, which I told you about. It's like a challenge, and all of you are gonna use one data set and you're gonna compete against each other to see who can get the highest score. Right, and that's kind of a fun exercise. And then the last thing, that's the second mini project, and then the third mini project will be during the week before finals, where you can do whatever you want. Just build some application in PyTorch, basically. Yeah.
I was going to say, can you talk about
No, in PyTorch.
Okay.
Yeah, and it can be anything, but you're gonna have to deploy it, and I'll show you guys how to deploy also PyTorch. And for this, we're gonna use Onyx, but it's very similar, GitHub and all that, all those things. So it's gonna be very consistent with that. Just, we need to use something a little bit different. Remember that PyTorch is the state of the art in terms of developing deep learning algorithms, okay? So today I'm hopefully going to finish Iris and motivate why neural networks are really important. So I usually mix up, most of it is for you guys to know how to do PyTorch, but we will do some things from scratch in neural networks just to kind of get some of the background going on, some of the main ideas. Any questions before we begin? All right, so we were, if I remember correctly, I have a new script for today, which is already on the GitHub, but I have, I think we did this one, NN, X, and matmul. I'm pretty sure we covered that topic. Oh, that reminds me, before I forget, exam 2 is a week from today, remember? So we are currently on week 11. Week 12 is next week, and that's exam 2 on Tuesday. Yeah. Remember, the exam is going to be similar to exam 1. It's comprehensive, right? But it's close notes. You're allowed your cheat sheet at 8.5 by 11.
All the exam we covered.
Comprehensive. So everything from beginning of the semester until this week. Yeah?
Let me review.
On a review. Do you have a question specifically?
What if, later on.
Machine learning, the machine learning pipeline. So a lot of questions probably about the project, things like that. And also some ideas of PyTorch and neural nets, basically. Yeah, Eric. Yeah, it's going to be similar to exam 1. Very similar. Word doc. Some questions could be just essay type, or there could be a coding example. Yeah. All right. Okay. So let's start. I already have the Anaconda environment set up. Okay. And so let's just start the Jupyter Notebook. So my goal for today is to do one example of iris, just to kind of, because I believe that's what we were doing the last time. Right, so iris torch MLP, you can see that there. I'm going to click on that script. This is what we started. Data, I created some random data, right? So we're going to need to basically have the iris data set. So that is, I have it here, so I'm just going to move it. So you use iris, correct, for the Weka project? We did some examples with iris. Oh, here it is. Iris CSV. Oh, I already have it. Okay, so that's the data set. You can see it now in my Jupyter, so you can just use the same file. It should be the same one I used before. We can open it basically, but now we're going to bring it into our Jupyter. Okay, so you can see it's got the classes in the last column, so we're going to need to change that. Okay, and we're going to build a neural net. So I have a few things in here, but I'm just going to kind of restart this. So I'm gonna, all right, so PyTorch, I guess I gave an intro to it, but I'll kind of summarize it again. PyTorch and TensorFlow are the state-of-the-art libraries for Python for the development of neural networks and deep learning, right? So they're like, when you hear ChatGPT and all that stuff, they were made, or ChatGPT was trained either with TensorFlow or PyTorch. So these are very powerful libraries. They basically interact with the GPUs and CUDA, okay? And the underlying thing that's running is C++, so it's very efficient and very fast, okay? So Python is really, just think of it as almost an interface to the C libraries in the background and the C binaries, okay? So basically PyTorch is this library called Torch, okay, and then we're going to be using several elements of this, like the NN element, which allows us to define neural nets, neural net objects, the functional, which will allow us to define certain things that we need, and optem, which will allow us to do the training, basically, okay? So all these things, these 4 little lines of code involve a lot, okay? So at today, it's not, my goal is just to kind of build one thing, get it to work, so that you know how it runs from beginning to end. And the rest of the semester, we're going to drill down into each of these, okay? Individually. But the goal today is just to get one of these running. Make sense? All right, so I'm going to go ahead and hit run here. Okay, and then XOR is the other problem. So these are the 2 problems I want to do, iris and XOR. Okay, so just kind of run through this. I kind of showed you the last time around that this is how you build basically these objects. We're going to take an object-oriented approach to build our neural network architectures. All right, so that basically means we define an input, a network architecture, and an output, right, and the processing of the data. Okay, so I'm going to repeat this again, but now specifically for the iris data set. So these were just examples I was doing before. And then I created some tensors, basically. So I was showing you examples of how to do tensors with Torch, just exactly how we did it with NumPy, right? So we created matrices and vectors with NumPy, if you remember, right? And think of Torch as just a group of people that copied NumPy, and they're basically doing the exact same thing. Okay, so I'm going to run all of these. All right, so that's kind of what we did before. Now we're going to start looking at iris. I'm just going to, this is our first example. build a neural net for the iris data set. Now, you guys already know, because you've used iris before with Weka, you know kind of the performance that you get with it, right? So you split it into train and test, and you're going to predict classes. And the classes are Setosa, Virginica, and Versicolor. Right, so I'm going to go ahead here, change the sound, markdown. All right, so we're going to start. Now I'm just going to reference my notes here. All right, so the first thing we want to do is we want to read in the data. Okay, so if you remember, I think there's several important libraries additionally to NumPy and Torch. Two of them are Pandas, and the other one is Matplotlib, right? So in general, whenever you're doing data science, these are the major libraries that you're using. Matplotlib is for plotting things. I will show you actually how nice that can be in the XOR example. We're going to use it for that. Okay. Pandas is, I think I mentioned this already. You guys have taken databases, right? SQL, and you know how to do these SQL queries. Well, Pandas kind of allows you to do some of those things like joining things, inner join, and all that stuff. Okay. So we're going to need to have that library. So I'm just going to add it here, and I'm going to say import pandas as PD. Okay. So I'm going to hit that, and that should be installed ready, right? So all of you have it, I assume. So hit run. And then I'm going to use pandas to read in the data. Okay. So I'll show you how to do this. So the data is in my current working directory. You can see that, so I don't have to specify a full path. This is what I had recommended that you guys always do, just to keep things simple, but especially on Windows and things like that. All right, so I'm going to go ahead and do path data. And that's going to be equal, just give it the name, iris.csv. Okay. And now I'm going to invoke pandas. So I'm going to say iris raw data. Okay, this is just the data. Raw data. And I'm going to use, I usually like, there's a lot of ways to read in data, but in general, I really like pandas. To read in the data, manipulate it. And then once I'm done with manipulating the data, I'll switch to NumPy and then Torch. But I mostly like to do everything here. Okay, it's extremely powerful. So I'm going to do read CSV. I'm going to specify path data, comma, and then the delimiter, I believe it's a comma. Yeah, the delimiter is a comma. Okay, and so let's go ahead and try and read it in. Okay, no errors, that's a good sign, so we have it. So now what you always want to do is look at your data. That's what Jupyter notebooks are for, right? It's like an awesome thing that you guys are lucky to have today, because you can really view the data as you're doing every step, which wasn't something you could do when you were doing scripts and things like that. So then here I'm going to now, because this is a data frame, I'm going to call iris raw data and should be able to view it. See, there it is. So there's my data. I know it's got 150 rows, 5 columns, right? I'm going to want to get rid of these headings. I'm not going to need them. I also don't need the index. Pandas by default creates this index. which is useful, but when you convert it to NumPy, you do get rid of it. And of course, we need to convert the Setosa string and the three class names into numbers, okay? So we're gonna need to do that. So let's see how we wanna do this. Iris raw data. So I'm going to show you a trick for this. There's a lot of ways that you can do this. You know, I've showed you label encoder. You could code something from scratch, or you can leverage the power of pandas and do this in one line of code. All right, so I'm going to go ahead and do that. So I want to convert, I'm going to invoke iris raw data. And now I want to reference one column. So I'm going to reference the column species, right? Because that's the one I want to modify. I want to change these entries, which are words, into the number equivalent, right? So I can do that in several ways, including something like this, species. Then I'm going to invoke iris raw data dot species dot map. And I'm going to provide in here a dictionary, a Python dictionary, like a normal Python dictionary of the word to the integer. So in this case, Setosa, colon, 0, comma, Virginica, colon, 1, comma, versicolor, colon, 2, right? Everyone with me? All right, so let's go ahead and hit run. Oh. Okay, so we ran it. Now let's run the data frame again. So I'm going to do iris underscore raw data. And as you can see, the labels have been changed. Does this make sense, guys? Any questions? So what I'm doing here is one common thing in data science is that there's more than one way to do everything, right? There's lots of ways of doing this. Here, I have come to really like pandas, although there is a bit of a learning curve with it, but there's a lot of power in it. Okay, so I definitely recommend. All right, any questions on this part? All right, so if you remember, Weka allowed us to use strings for the labels, but in PyTorch, everything needs to be a number. Okay, everything needs to be a number. So now we're going to go ahead and just do a couple of things, a couple of tricks here. So that we can build our neural network. Yeah, so this will be a very complete exercise. And it's going to take us all the way to the confusion matrix and the scores accuracy, precision, recall, and F measure that you got when you were doing Weka, right? So you did this in Weka. We're kind of repeating that same exercise, but everything in PyTorch, okay? Please stop me. I will post this Jupyter later on the repo. So don't worry about that. But please stop me at any time if you have questions. I'm going to go through the entire machine learning pipeline. Okay. So, but hopefully we should be finished today. All right. So we've converted the labels into strings. Now let's do a few more things. Let's say that for some reason you want to print out these label head, the column headings, right? So you can do that from pandas. You can create a list called headers list. Headers list. And you can invoke iris underscore raw underscore data, right? And then you're going to say dot columns dot values and then to list. Okay. So then I'm going to go ahead and, oh, and then I'm going to print, I want to look at it. So I'm going to do headers list here. Hit run. And that's basically the column headings. Okay. Now I want to create what is called a correlation matrix. So a correlation matrix is something that is very useful to see how variables are correlated in machine learning. So think of this scenario, right? You have 10 variables, but you find that all 10 variables are pretty much correlated, right? Have a linear correlation. That basically tells you that honestly, you just need one. If you just use one variable, you'll get about the same results, okay? So that's kind of something that's useful when you're doing data science to explore these variables here. All right, so we're going to need to add, we have NumPy, but we're also going to need a library called MLXten. So let me see if I have this already. I'm going to do from MLXten. I'm going to, and then it's going to be dot plotting. I'm going to import something called a heat map. And this is just because it'll present the correlation matrix. It'll be more, nicer to look at. So I'm going to go ahead and hit run here. Okay, so the library is not there. So we need to install it. Just going to do that from the Jupyter Notebook. So that should be pip install MLXten, just like that. Okay, I'm going to go ahead and hit run. Okay. So you want to check everything successfully installed. So now you can comment this out. And now we can go here and run this. Give it a minute. All right, it finished. So we have the library now, MLXten, so we can continue. So now we should be ready to create a correlation matrix. This is very useful when you're doing, when you're exploring your data. So we did feature ranking, if you remember, in Weka, but we didn't do this. Okay, this is a different thing. So let's go ahead and try to build this up. So I'm going to create an object called CM, correlation matrix. Okay, I'm going to invoke from NP, which is NumPy, the core coef function. And I'm going to provide to it iris raw data. Iris raw data. I'm going to, so once again, I'm showing the power of pandas here because we could do this correlation matrix for just 2 variables, 3 variables, these variables, and these other variables. So you can do that by simply creating lists of the variables that you want, the columns that you want. In this case, I'm going to do it for all the ones in here. So this is how you can index in pandas in a more intelligent way by just providing a list of the columns that you want to look at. Does that make sense? So that's kind of a nice feature, I think. And then now that we've added this, we're going to say that from this pandas data frame for those columns, I'm going to do dot values. And so I want that, and then D, transpose. All right, so that should create the CM. MP is not defined. Okay, I don't have NumPy, so I'm going to do import NumPy as NP. Okay, so run that as well. Okay, so that worked. Hit run.
X instead of a Y for broad data.
Where? Oh, yeah. All right. Thank you. Good catch. Yep. No, good. Thank you. All right, perfect. Good catch. All right, so we have our CM correlation matrix, but now we want to look at it in a really nice way. So we're going to use a heat map, basically. Okay. Heat map will provide like a little grid so that we know when something is stronger or weaker. All right, so now I'm going to go ahead and invoke, and I think I don't have matplotlib, so I need to import that library. Usually, whenever you do data science, pandas, matplotlib, torch, and numpy. It's going to be and then a few other ones. So I'm going to create this HM, which is the heat map. I'm going to invoke heat map from mlextend. I'm going to give it CM, which is the thing I just created with numpy. And then I'm going to tell it that I want for the row names, row underscore names, I want it to use the headers list because I'm correlating the columns to themselves. And then obviously for the columns list, I'll do the same. So column names equal headers list. Okay. And then finally, we specify the figure size. So figure size equal 20, 10. All right, once that's done, we should be able to invoke plt.show, which is something, again, all these things maybe are new for you right now, but very repetitive, okay? When you're doing your Scifar 10, you'll be using pretty much the same things. And when we do XOR, you'll be doing the same thing, and I'll do a few other data sets in between. Okay, any questions? All right, so now I don't have matplotlib, I'm pretty sure, so let me add that in. So here I'm going to say import matplotlib dot pyplot as PLT. Right. All right, so it worked, no errors, that's good. So now we should be ready to see our correlations matrix. So let's run it. And there it is. That's a very nice, yeah, it's kind of big, but that's your correlation matrix. So what does this tell you? It basically tells you the correlation between two variables. So for instance, you can see it goes from -6, there's a 0 there, to 1, right? So basically what this is telling you, if it's 1, is very positively correlated. If it's minus 0.6 is negative, very negatively correlated. And if it's 0, there's no correlation. So you can say, for instance, like if it's a yellowish, right? That's why it's a heat map, like very hot. So these, you can quickly say which ones are strongly. Obviously, the things in the diagonal are that variable to itself. So that's going to be very highly correlated. You should ignore those. But this one, for instance, this one, right, is highly positively correlated. So petal width and petal length, which makes sense. Do you see that? And then negatively correlated would be things that are very dark. So probably whatever this is, the species and sepal width are negatively correlated, which is also a good thing, right? The problem is when there's 0. So 0 would be what? Do you guys see anything that could be that, like a 0? What color is that? Like a green, dark greenish, bluish? Maybe this one,
If
right?
species were correlated with each other, it would be very hard to differentiate them.
Say that again?
Like the species, it was very, they're correlated with each other a lot. That probably means that like,
Which species? Because we only have here the features and the column for the labels. And we don't have the individual species, if that's what you mean.
Oh.
We don't have Virginica to Setosa or something. Yeah,
So for no 0 and negative, is it saying like 0 is, it couldn't decide either way? if there's
yeah,
total?
0 is not useful.
Okay, and negative meaning like. just
Negative
total?
is useful. It's
Okay.
just in a different, it's like, what's an example of something that's ice cream consumption and how cold it is today? They're negatively correlated, right? So ice cream, when, really high cold, very low ice cream consumption, very high ice cream consumption, very low cold. Yeah.
so would you just like multiply by -1 or something? Just change the direction?
Well, you want the direction though. The direction tells you something, that they're negatively
I
correlated.
was thinking like running a can or something. Would you?
This is not for that. This is just to see the relationship between the variables. This is not the classifier at all.
Okay.
This is just you doing some data analysis to kind of see what's going on, but this is not gonna go into the machine learning architecture.
Okay.
The machine learning architecture will discover this on its own, if that's maybe what you're thinking.
Okay.
The neural nets will, in the weights and something like that, but that's different from this. This is just you initially looking at the columns and trying to see what's, are there correlations?
Like two features correlated, does that mean you like remove one of them?
Yes, exactly. That's a good point. So that's what I was saying. So if two features are highly correlated to each other, I mean, you can remove one of them. Especially if they're expensive.
And that's because like sometimes machine learning algorithms don't scale well with dimensions.
Yeah, I mean, if you have RAM issues, for instance, or just because, I mean, you don't need it. One is enough. Make sense, guys? All right, so this is one thing you should be aware of. So this is correlation matrix. Again, we haven't started building up our neural net in any way. This was just something that, a lot of people like to see. Believe me, when you want to see your variables and get a feel for how they. All right, so now that we've completed that part, let's continue building the pipeline. The pipeline, honestly, it's going to start getting repetitive because we're always going to be doing the exact same things, train, test, split, and all that stuff, similar things that we've done before. All right, so now we're going to convert this pandas data frame to NumPy. So I'm going to say iris raw data. And, by convention, some people will add something like that just to say that's a NumPy now. So we're going to read it in from the pandas data frame. So I'm going to say iris underscore raw underscore data, right? That was the iris raw data. And pandas has a built-in function called toNumPy. And so everything that you know about NumPy, you can flattening and all that stuff, you can do here, okay? So now we can take a look at this. So now basically it's the same data, but the format of it has changed now, as you can see. So now it looks like a NumPy array, okay? And what do we have to do now? Notice that we've got the labels and the features in there. So we're gonna have to do a slicing, right? Slicing. So if you remember, slicing comes back once again. All right. All right, so we want to always print the shape. So this is something that you want to get it. Maybe this is pretty easy, but as you start doing other things, it gets more complex. So iris raw data underscore NP dot shape. Hit run, and there you go. So it's got 150 rows, which are the samples. It's got 5 columns, of which the last column are the labels. So now we're going to slice, and you guys should be able to do this by now because we've been doing this all semester. So I'm gonna create my X and my Y. See how this, even though we're building a neural net now, we're still using the same things. Okay, so Y. Remember, by convention, the X is uppercase, the Y is lowercase. So I'm going to invoke iris raw data underscore NP. I'm going to do this from the NumPy matrix. And how do I slice the first 4 columns? Colon, comma, -1. All right, so this allows, this basically is excluding the last column. All right, or sorry, it's going from beginning, right? The first 4 features. It's excluding the last column.
Do we want to also exclude like the first column too, if that's the idea?
No, because I already converted it from pandas to NumPy, and notice it's not there. It's a good point, but it's not there anymore. All right, so now we're going to do the same for Y. So iris raw data underscore NP. Once again, we're going to slice all rows, and we're going to just need the last column, right? So that's going to be 4:5. Do you guys see that? Yeah. So we've got the Y and we've got the X. Okay. So here I do the same thing all the time. I want to print the shapes. I'm very obsessive about that. So X dot shape 154. Y dot shape 151. You can also print the Y just to see the data in there. Always a good idea. And you can see the columns are 0, 1, and 2, and that's what should be in there. Okay, everyone with me? All right, great. So now we can keep going. This is the machine learning pipeline. All you're doing is converting the data into the appropriate format. So I've got Y here. All right, now this is something that I like to do. Weka does it, and I like to do this. So I'm going to print a histogram, okay, of my data. And I'll tell you why it's a good idea to do that. Okay, you guys know what a histogram is. All right, so I'm going to use NumPy again. So I'm going to, oops, sorry. All right, I'm going to do the set, just create a set. So I'm going to say numpy.unique for Y, all right? And then I'm going to print the set. I'm going to save it at this point. So you can see my set consists of 0, 1, and 2. Those are the 3 columns, okay? So what I want to do now is I want to create a histogram so I can see the class balance or imbalance. Okay, what that means is I want to know that, you know, the classes are balanced, that one class doesn't dominate over all the other ones. This is really important in machine learning. So I'm going to do here. I'm going to, from matplot, which is PLT, right, has a very handy function called hist for histogram. So I'm going to do the following. This should be an underscore. Whenever you do this in Python, it basically means that no variable. It returns something, but it's ignored. Like when a function returns a variable, but you're ignoring it. All right, so then I'm going to do plt.hist. Okay. And I'm going to give it Y, which is the data. And I'm just going to tell it that I want it to do bins equal auto. It's the default thing. Auto. All right. And you can put a title if you want, but I'm going to skip that part. And I'm just going to do plt.show. And that gives us a nice histogram, similar to what Weka did for us. And if you remember, basically this is a count of the number of times it sees one of the classes. So for the 0 class, there's 50 samples. For the 1 class, there's 50. And for the 2 class, there's 50, for a total of 150. This is really useful so that, you know, for precision recall, right? This tells me accuracy is good enough as a metric. But if there was a high imbalance of 1, then you have to look at F measure and all the metrics really. Okay. But Iris is like the easiest data science data set. All right, so I did that. Notice, you know, mostly just data science things. We haven't really started defining our model. I already printed the shapes. All right, now we are ready to do the train test split. How do we do that? We do that with sklearn. Yep, sklearn. I'm going to continue using sklearn. So I'm going to need to, I don't have that library, I believe. So I need to bring it in. I like to put, some people put the libraries wherever they use them. I like to have everything at the top. So that way I know exactly what I need when I'm building something new. So you can do here, import sklearn just in case. But specifically, we're going to say from sklearn. From sklearn. Dot model selection underscore. So dot model selection. Import train test split. All right, so that's our familiar function. So we can go ahead and use that. Hit run. Okay, no errors. That's good. So I'm going to now use it. But before that, I like to set a seed that changes every time I run my Jupyter. And that's just so that every time I run it, I can see the results and they're going to be a little bit different because I've randomized the data different. But if as I'm debugging something, I'll probably run it 5-6 times. That's almost equivalent to 10-fold cross-validation if you think about it. And you've looked at the data. So for you, it gives you like a little perspective of what's going on. So I'm gonna do here. So I'm gonna create a random seed, random underscore seed. And I'm gonna say int. And then from here, I'm gonna do random dot random. So this just brings in like a decimal, and then I multiply it times 100, and that should give me a value between 0 and 100, basically. But it's a random value every time, so I can use that so that the randomization will be different every time I run the Jupyter. All right, I need that library. Import random, hit run. There we go. Now I'm going to do the train test split yet again.
Go to the standard library.
Huh?
I thought just like it shouldn't like
Say that again.
like you clearly defined it as like random.random. I thought you just like detect automatically that hey, I'm looking for random standard library or something.
Well, it's got several though. It's got like randin, so random dot randint, rand float, rand this and that. So it's very versatile.
But like it should let you do that without importing it, the library name. Like I don't know.
It should be a built-in library, is what you're saying?
Yeah, either that or like if you put random.random or something, it should know that you're looking at for the random library.
Call them and tell them that. Maybe for Python 4.
Okay.
All right. So let's go ahead. So now we're going to split our data, right? So this is the exact same thing we've done before. So X train X test. Notice it's very consistent to what we've done before. Y train, Y test. And that's what I like, you know, that you should always try to have this consistency, because at some point it's almost like tedious, you know. And so that I strongly recommend that you follow these type of template approaches. All right, so we have our 4 variables, and now we invoke train test split. I'm going to plug in here X, comma, Y, and then the test size. So test size will be 0.2 in this case, right? 0.2. So that, what does that mean? It means that we're splitting the data into train, 80% for train, 20% for test, okay? And the random seed will be random seed. Got it, guys? So we're randomizing the data, then splitting it. 120 will go for training, 30 will go for testing. Okay. Yeah.
Random state.
Random state. Oh yeah. Thanks. Good catch. Thank you. All right. So hit run. There you go. Our data is now split. We have the 4 things that we need. Usually here, I'm actually I'm typing this. I'm going to start copying it because it's going to be very verbose. Hope that's okay. So I'll add this Jupyter later, but I do have it in a different place. So I'm using this right now, but when I finish this one, I will upload it to the course repo. Okay. All right, so I'm using this one actually. All right, so this will just make this easier so I don't have to type all of this. All right, so we are basically at this point, we printed the histogram. I did the train test split. Now I'm just going to copy this so I can print the shapes. I'm going to go ahead and do that. Right? So I'm just printing for X train, X test, Y train, Y test, the shapes. And this should be familiar to you. It should be 120 by 4, 130 by 4, and so on. Questions? We've done this before, so it should be easy. Okay. Now, here's something interesting. We can look at data types. Even though Python doesn't have data types, NumPy and Torch do. So I'm going to do X underscore test dot D type. And you can see it is a float 64. This is important for several reasons. As you start building neural networks that are really large, they're going to be very big, right? You've already encountered this problem, for instance, on GitHub. Let's say that you were deploying this model to GitHub, right? And it's over 25 MB. Why is that? Because you're using very large variables. So one easy solution is float 32, int 8. That's called sparsity and quantization. And these are tricks that you do to reduce the size of the files. Do you guys see that? But anyway, this is in my example here, I will want to change this data type. So I'll show you how we can do that. Okay, so we did that. Now I'm going to copy for the Y. Remember, the Y is made up of integers. So I'm going to run Y test D type, and that gives me Y test. I guess these are float. Yeah, these are float, aren't they? How did I do this? Ah, okay. Yeah, I missed a step. I should have changed these to integer. So labels should be changed to integer. In general, it's a good idea. So where should I do this? I'll do this before this part. Okay, here. Okay, if you notice it's float, but I forgot to change it to integers. So let me go back here. There we go. So I'm gonna use this to convert it to integer, and I'll just repeat that step. So I'm going to take y, right, as type int, so that instead of floats, it'll be integers. Right? Let's run this again. If you notice, they are integers now. Questions? All right, so all these things are really important. So now if you look at the set, I'm going to change it. They're integers. The histogram doesn't change, but that's okay. Initialize the seed. See, here you go. You run the seed again, just because you're always debugging. Train test split. Shapes again. This one is float 64 still. This one should be int now. You can see it's int 32. Okay. All right. So in general, I would recommend changing PyTorch. So we're about to move to PyTorch. Okay. We're about to do that. This is float 64. It's like too big. It's unnecessarily big. So you can change it to float 32. Okay. So you can do that in NumPy. And sometimes this can also give you an error. And so it's a good idea to kind of deal with it. So I'm just going to copy it actually from here. So I'm going to do this. I'll explain in a second. All right, so I'm going to take xtrain and xtest, and I'm going to set the data type, notice, to np float 32 before it was float 64. So I'm just changing that, reducing the size. For the ints, you can make it, I guess this example makes it actually int 64. So that's fine. There you go. That's it. Now we are ready to convert everything to Torch. Okay, so this is, in the pipeline, we can go ahead and take our NumPy arrays and convert them to Torch tensors. I'll do control copy. Control V. So notice all we do is we invoke Torch, the function from NumPy, and we take xtrain, xtest, ytrain, ytest, and now we're converting it to Torch. That's the state of AI today. You switch from data types. Go ahead, Henry.
And that just gave you like a tensor or something, right?
It's a tensor, yeah. I mean, the NumPy is still a tensor. It's just in NumPy. This is a tensor is a math term, and these are just data structures.
It's just like a D-dimension array or something.
It's well, the X is a matrix, and then the Y's are vectors. But yeah, we're just switching from data types, right? So or from data structures, if you will, because we need. So one thing that you definitely need to happen is whenever you're building a neural network in Torch, everything needs to be Torch. If you try to like use some NumPy thing, it's not going to work. It's going to give you an error. Right, so we are now doing this task, right, of converting the 4 into Torch tensors. I'm going to hit run, and that's it. They're now Torch tensors. We could normalize our data and all of that. I'm going to skip that part for now. Yeah, go ahead.
One way to normalize it would be you take.
This is why I'm skipping it, because there's some equations involved, and so we're going to cover it later.
Of each data.
Say that again?
Like, you want it to be like between like 0 and 1, right?
Yes. In machine learning, you really want everything to be normalized all the time. That provides better results. But Iris is easy enough that we don't need to do that right now.
Right.
And currently, this would just add complexity to this. So I'm gonna skip it.
With the strategy though, if you were. to
There are
normalize
two
it,
strategies.
Just multiply by the reciprocal, take the reciprocal of it, of whatever 20.
Henry, so for me to like properly do this, I would formally do it, right? So I would define what the normalization equation looks like, what the standardization, and go into that. But I'm trying to skip that to avoid complexity right now. But I promise I will address this later because it's extremely important. As if you want to win Sci-Far 10, I recommend you normalize. You see what I'm saying? So that's the whole point of Sci-Far 10. It'll motivate why all these things are necessary if you want to win that 3D printed trophy that I'm going to make. You know what I mean? So, all right. So anyway, good. All right. So I'm skipping that part for now, but I will address it later on. And it's in the Jupyter. You can see it. It's right here. This normalization I'm skipping for now. All right, so the next thing we're going to look at is creating this thing called a data loader. So we could read in the data ourselves from scratch and do all that process. But that's then a lot of code, right? And so PyTorch has this thing called data loaders. And data loaders, if we learn how to use them, are very useful. Okay, so I highly, pretty much, you should always use them, and master them. So I'll show you today how we can get started. So that's the next thing I'm going to do, which is this thing called the data loader. So I'm going to even add the heading here, create data loader. As I said, this is a PyTorch construct, okay, that has been built to handle the data, and think of it as from there you're going to be reaching in for your data. Okay, so Markdown, run. Okay, got a few more cells here. All right, so we are ready for that. So again, I'm just want to print out shapes and things like that. I always like to know the numbers. So I'm just going to grab xtrain. And I'm going to say that I want the shape 0. So that's the number of rows in there, which you should know is 120, basically. Okay, so I know there's 120 in there. Now, I'm going to create 2 lists, basically, because the data loader from Torch takes these lists in a specific format. So once again, with data science, machine learning, it's always about taking your data and converting it into the appropriate data format. Okay, and that's what I'm going to do now for the data loader. So I'm going to create iris underscore train underscore list. And I'm also going to create iris test underscore list. You guys see that? So I'm creating these 2 things. These are just going to be the inputs to the data loader. All right, so how does it work? So you guys remember at some point we discussed what a list comprehension is, correct? Yep. Quentin? Yeah, all right, perfect. So I'm going to use a list comprehension here, okay? And it's a for I in range, okay? And the range is going to be that 120, all right? So I'm going to iterate through that for the train. So all I have to do is say xtrain dot shape 0, right? This is the same thing as here, basically 120, right? So I could hard code 120, but it's not a good idea. All right, so this is the list comprehension. So now I'm going to remember I is the thing that goes in. And so now I'm going to create tuples. So this is the trick that you have to, if you're taking notes, grab your notebook, right, and write down. You're creating a list of tuples of the features and the label. So tuples are 2 things, like a list of 2 things. It's called a tuple in Python. Okay, so you're creating a list of tuples that has 2 elements. One is the feature vector, the other is the Y. And if you can take your data and convert it into that, then boom, you can get it into a data loader. Yeah.
And can the Y vector, like, say, have like multiple labels? Or like,
Currently, we haven't, so here's the fun thing about this, right? So usually neural networks use something called one-hot encoding, but nowadays, they're so helpful that we can just give it the 1, 2, 3, and it'll automatically convert it to one-hot encoding. So this will just be an integer, basically. Yep. And again, I'm still typing this thing when I should be. Sorry, it's shutting down. I'll start in a sec. All right, well, it's starting, so I'm gonna go ahead and just copy this, okay? So remind me if I'm typing this to just copy it. All right, so because I do want to finish this one today. All right, so again, what I'm doing is I'm loading my data into these list of tuples, so I can load it into my data loader, which is this construct, okay? All right, there we go. So, no, I'll explain again. A tuple is basically that's a tuple. So if I put 3 and 4, 5, 6, that's a tuple, two things, right? That's a thing in Python. So that's what I'm creating here. What I'm putting in there instead of 3 is this, xtrain tri. So what is that? That's the first row, right? That's the first row of it. And what does the first row contain? It contains the feature vectors of iris. And so we can see that here. Right, so I'm going to plug in instead of I'm going to say like 3. If I do that, you see that's a tensor of the features. Petal width, petal length, sepal width, sepal length. Make sense, guys? Questions? All right, so I'm creating these tuples where I have a vector of 4, and then I'm going to have the label. So I also want to copy this one, just so that you guys can see it. The corresponding one would be 3. So if I hit run, you can see it's got label 1. Okay, so now I'm creating the vector and the label. That's one tuple, then another one of the next vector and label, and so on. And I'm creating this list here. Got it? All right, so you can also view it by, I'm going to do this. So now I'm going to get rid of this because that would error and mess things up. All right, so I did the list. Now we can look at one list, this one that only has 30. And you can see it's got basically the vector and the label 2, the next vector and the 1. Since you guys have done KNN averaging, you're experts at this now, right? So you're experts at looking at these vectors, doing the Euclidean distance, and you understand that that's a point in an R4 vector space. Make sense? Because that's iris. All right, so we did that part. So now that we have our lists created, the next part should just be to simply create the data loader. Okay, so I'm going to grab this one here. Now, this is a library in Python. So if you notice, it comes from Torch, utils, data loader. Okay, do you guys see that? So it's just a thing that was developed by the PyTorch people that make our lives easier. Okay, in one line of code, if you create these lists, you're done with like a lot. All right, so this is going to take in, notice, iris train list, because we're going to have a data loader for train. So I'm calling it train underscore DL for data loader. That means I'm going to create another one for test called test underscore DL if I want to. What's really nice about this is notice that you're going to give it the data, it converts it into the data loader, but you also specify some parameters, such as something called the batch size. So I need to specify what that parameter is. So for iris, because it's very tiny, my batch size was only 16. But when you do Sci-Fi 10, the images are colored, right? And so, and there's a lot, there's like 60,000 of them. So when you're doing that, you won't be able to load all of it at once into the neural net. It's not going to work. In general, you can't do that. So what you can do is you can give it batches of data. Imagine like, remember in the old trains where they had all the coal and then you would shovel in and throw some in the furnace and then do another one? That's what we're doing, but with data. That's what batching is. So you're grabbing data, throwing it into the neural net, another batch of data, throwing it into the neural net, and this is how they train. So this is how you could give it 1 billion samples of data, and you could train a neural net because you wouldn't give it the 1 billion samples at once, but instead in batches. Got it? That's the beauty of this. So here I'm specifying that I'm doing batches of 16. So that basically means it's like you shovel 16 pieces of coal, then another 16 pieces of coal, and you keep doing that until you're done. Okay? Got it, guys? The other thing that's going to happen is notice that you have this other flag called shuffle. And that means the following. So whenever we train machine learning, right, we're going to have 2 for loops when we have the main loop. One is called the for loop for the epochs, and the other one is the for loop for the batching. So the for loop for the
Epoch just means iteration over training set, right?
yes, exactly. That's yeah, nice. Thank you. You like gave me the words I was looking for. It's exactly what Henry just said. Epochs, that first for loop means one run through the whole data set. So if you say I want to do 1,000 epochs, that means that the neural network will see the data 1,000 times. When I first learned about this idea, for some reason, I thought it was cheating. I don't know why, like instinctively, why am I showing it twice? It should learn, right? But you actually do this in machine learning. You show, machine learning is not like us, right? If I trip on this, that's it. I'm never tripping again because, especially if I get hurt, right? I know it's there. I learned with just one example. The analogy here is that machine learning would need to trip on this 1,000 times before it learns not to trip on it. That's what epochs are. You give it the 120 samples 1,000 times. But every time that you start one iteration through the whole data set, you shuffle it. That's key. So it's not always seeing the data in the same order. In fact, every epoch, the data has been randomized different. Yeah, Henry.
The reason why you don't want to overfit your data, right?
Yeah, maybe. I mean, it just works. I can tell you experimentally, it's a good idea to do that. Yeah. All right. Got it, guys? Yes, sir. Yes, every time that you're going to start one run through all the samples, you shuffle them. And then you're going to scoop from them. It's almost like in the train analogy, right? I have 120 calls. So I grab 20 at a time. And I do that. And I finish. And then somebody like grabs the 120 and mixes them, puts them back in. And then 120 at a time. Finish. Mix them up. And so on. Yeah. And that's a good practice in machine learning. So that would be a lot of code if we had to do that. But it's nice that we have data loaders because you determine that. Well, Sci-Fi 10 will tell you how many epochs you need to do. A lot of these things are, like experimental. You kind of have to try it out. But what's going to happen is you're going to do 10 and you'll be at 60 maybe, and you're going to be like, I'm going to give it more epochs. You know what I mean? And then you're going to be on your laptop and it's going to take 2 days and you're going to be like, you know what? I didn't want to get on the GPU Scholar, but I am going to get on. It's kind of like, so out of necessity, you do these things sometimes. All right, so any other questions? All right, so let's go ahead and create the data loader. All right, so the data loader should be created now. Well, you can look at it if you want, but it's just going to be a torch object at this point. See, torch utils data loader, basically. It's like a serialized kind of a thing. It's meant to be very efficient, so it's written in such a way that it's efficient. All right, now we're going to do the same thing for the test data loader. All right, so once again, list comprehension. We did that up here, actually, right? So we have iris test list. So notice I'm providing iris test list now. I'm calling it test DL instead of train DL. And I'm providing the batch size. I'll talk about this in a sec, and then shuffle true. So this batch size is different. The reason being is you only do epochs during training. For testing, you just need to do it once. So really then here, batch size is all test data, basically. And all test data is 30. Does that make sense, guys? So you're just going to give it all 30 samples at once, and it's going to give you the performance metrics. I mean, I could have just written 30 here as well. Thanks. Got it? All right, so I'm going to hit run. All right. So believe it or not, we are ready to build our neural network architecture. So what I'm going to do here is, you guys were familiar with the MLP, right? That's the one that you used in Weka. So that's, you can see neural network architectures. After you do all of this, this is where the neural net comes in. We're going to do an MLP like the one in the Weka software, and then we're going to do another one, which is going to be deep learning. So whenever you hear deep learning and everything, that's what this is, okay? And I'll show you the two architectures. So what's really nice about doing this in an object-oriented fashion is you can literally just copy-paste the thing and plug it in like a little module. So I'm going to throw that in there, and I'll explain the code. Oh, sorry. All right, so let's do the MLP first. And again, I will come back to this, and we're going to go to even very basic ways and build up. But today I'm just showing you how to build a neural network that works. So this is the network architecture. I think I did discuss this the last time we met. It's got two functions in general, the init function and the forward function, okay? So you define a class. You can give it any name you want, such as MLP_net. And it's going to have this in here, nn.module. What did I say this was? Do you guys remember in the last class? It's a feature of object-oriented programming called class inheritance. Okay, and what that means is just a concept you've seen before. It means that you can take another class and inherit all the properties of it into your own class so that you don't have to define them. You'll learn to appreciate it. I mean, it's really nice. So then now all you have to do is you have the init function, which is the constructor, where you specify what you're going to be doing. Okay, you're going to specify the initialization of the variable. So I'm actually, since I didn't do scaling, I'm going to take that out. I'm going to get rid of this to keep it simple. All right, so should be simpler now. So the first thing is, you call this function superinit. This is just invoking the constructor of the inherited class nn module. That's it, right? So you invoke that. Then after that, you're going to define the architecture of your neural network, okay? I'm going to get rid of dropout for now, also, just to keep it simple. And we're just going to leave it like that. Okay, that's a neural network. And I'll describe on the whiteboard what this means. I'm going to get rid of this. Get rid of the dropout. All right. So that's our first neural network that we're going to be building. So I'm gonna switch to the whiteboard here. Okay. So what we had talked about this before, right? So what is a neural network? It's got an input layer and an output layer, right? So we're doing iris. So it means that we know some of this information already, right? So what is the number of neurons in the input layer for iris? We know that iris data is like this, right? It's got F1, F2, F3, F4, and then we have the class, right? So basically this here goes in here. So that means we have 4 values. So our neural net will have 4 inputs. Does that make sense, guys? You have a question, Henry?
No.
Yeah. What is, so by this logic then, here, we have how many classes? There's 3 classes, 0, 1, and 2. So you should think that this is going to be represented now as a vector of 3 neurons for the 0, the 1, and the 2. Do you see that? Okay, everyone with me? So you're predicting 3 classes. So this is the input layer. This is the output layer. Because it's a multi-layer perceptron, we're going to have a layer in between. And this is going to be called a hidden layer, hidden one. So in this example that I'm using, that I define that to be 3. But you really can define it to be whatever you want. So let's change it to something like 6. So how do I? Sorry. That's still there. All right, so I'm going to say that I want this to be, actually, let's make it 5. Remember, these are going to be fully connected. Do you see that? So what that means is this neuron is connected to the other neurons that are coming. That's a neural network, basically. We covered this in the last lecture, right? Where we talked about the weights and how, everything was mapped. So that means that we know these dimensions. So we have 4 neurons in the input, 3 neurons in the output, and 5 neurons in the hidden layer, right? So we want to create this neural network, but in code, right? And it's going to look like this. So I'm going to hit stop share here. And now I'm going to define it in the code. So that's what this does. So we're going to have one initial layer that takes in something that is of size 4 and does what? Maps it or transforms it to something of size. How many neurons did I put in that hidden layer? 5. So I'm going to change this to 5. Do you see that? That's it. Now I need to do the next one, right? So the mapping from the hidden layer to the output layer. So that's what this is, linear 2. Okay, so I'm going to do what? It starts where it left off. So that means 5. Do you see that? And then it ends in what? 3, because it's predicting 3 output neurons. That's it. That's the whole magic of this. If you understand this concept, you'll be able to build any neural network that you want. Does this make sense, guys? Yeah, go ahead.
How do you do the optimal amount of layers?
It's experimental.
And how would, okay.
The bigger your data set, the more layers probably, the more parameters. But for iris, which is so small, this is more than enough. You see that it's kind of like that. Got it? If I give you, Henry, a problem to solve, you're going to take X amount of time. But if I give all of you to work together the same problem, you have more capacity, right? So you'll do better. And that's kind of the idea of making something deeper, is like giving it more brain. Okay? All right, so we're defining the architecture. So I'm trying to define that neural net. So now, what do? This is just where we define all our variables as usual in object-oriented programming. This is actually the forward function, that what is called the inference. So input goes in and you predict something. So the input is X, right? You see that here, that's the input. X will go into the function self-linear 1. What is self-linear 1? 4 to 5. What is the size of X? 4, correct? Because that's the input, goes into 4. And so now this X here will be the initial vector of 4 transform into a vector of 5. You guys see that? So now that becomes the input to the next one over here. So linear 2. So that's 5. And when it comes out, it is 3. So it's going through the neural network like that. So X goes into this function, comes out, then it goes to this function and come out. Now, what is this activation? So in between, I added something, obviously, right? And I have to talk about that. So that's really important. This is this function here. So self act 1, right? And it's basically something called the sigmoid function. We will drill down into this later on, but for now, just think of it as it's transforming the data. It's like scaling, but it's different. So I'll give you an example of this in the whiteboard. That actually is really important, as that's what the number of layers and that activation is what creates a neural network. Without that function, you would not be able to get a neural network. You need to have that. So what does that mean? So the sigmoid is a function that basically does something like this. Oh, sorry, it's sigmoid, right? So 0 to 1. So this is minus infinity to plus infinity. So that can be any number. But when that number from minus infinity to plus infinity goes into that function, it'll always get mapped into something like that. What does that mean? It means that if it's minus 1,000, for instance, it'll get transformed into what? A number very close to 0. Do you see that? It never quite reaches 0. Does that make sense, guys? And then what if the number is, plus 2,000? Then it'll never quite reach 1, but it's getting very close to. So it always compresses into 0 and 1. And this is just one example. So obviously, if the value is 0, it's going to be 0.5. So that's what these activations functions do, is they're just transformation. There's another one called a ReLU, also known as the hockey stick. And basically what this function does is something like that. So really it's here, right? So the output, this curve here is this one, like a hockey stick. So what do you think this is doing? If the value is minus 2,000, 0. And if it's, and this is linear, so if this is 2,000, then it's 2,000. It just keeps going. So effectively, what's it doing? Getting rid of negatives and just keeps the positive. This one is actually it's the best neural network activation function. We'll see this later. But anyway, hopefully that made sense. That's what we're doing. We're just transforming our data. Yeah.
Sigmoid was the best.
No, ReLU is the best. ReLU, I mean, yeah, in general, I would always try ReLU and then go with that. Any other questions? So yeah, as I said, I will come back to a lot of these concepts, but this is kind of how you build a neural network. Yeah.
How does it calculate
The what?
the next value, the sigmoid function calculate the next value?
Because it goes, so act 1 is this, right? Which is defined as sigmoid over here. So then I take X, it goes into linear, and it just changes dimensions. But that X goes into this, which is sigmoid, and now it is transformed.
From negative,
From normal numbers into a range between 0 and 1.
0.
Yeah, yeah.
But how does it translate to 0?
There's an equation for it. I don't have the equation with me right now. I will cover that. Yeah.
How come we use the sigmoid, like if the rally is.
Why am I using sigmoid here? Just to show you. Just to show you. This is not normalization. This is the activation function. It maps something. That's why we're going to do the XOR problem. And the XOR problem, I will do this. Which means we're not going to have activation functions. And effectively, we will not be able to solve. I'll show you that the learning algorithm cannot solve the problem. When we add these sigmoids, we'll be able to solve the problem. And then, huh?
What is it?
The XOR problem is the classic XOR, like in the truth tables.
And what is?
It's something that cannot be. It's so okay. XOR, we're going to cover this. It's the next
You
thing.
know what the binary operation XOR is?
That's exactly what it is.
So just predicting whether.
So think of this analogy, okay? Linear means a neural net and no neural net, right? How about that? So if I have data like this, and I want to build a line that separates it, I can do that, right? And I separate all of the cases. But what if I have data that is not like this? And instead, it's like this. Yes, calculating the line of best fit. That's what we're doing. That's what neural networks do. Find me a line that separates these perfectly. Is there a line that separates these perfectly? If I do this, some is classification, right? I can't do it. So, but a neural net can solve this. So what we will see is the neural net, just to give you an intuition right now, the neural net would be able to do that. Magic, right? So because it can create these functions that are like curvy like this, which a line cannot. So that's why we add those experiment, and we'll see that later. So those are a lot of concepts, guys. So, we'll get to a lot of those. Yeah.
It might be like multiple functions, or find the most efficient one.
Yeah, it's so what a neural network is by definition is called a universal function approximator. It means in theory that it can approximate almost every single function in the universe. Think about that. Your brain could be a function, right? And that means it could approximate it in theory. Do you see that? I mean, it's literally a universal function approximation theorem that says that neural nets can approximate any function. Almost any function. How about, I don't want to say every function, but almost every function. So they're very powerful. And so that's what we're going to be exploring both experimentally and getting into the theory. Once again, all I'm trying to do is build one right now. Yeah, go ahead.
And we'll be learning how to be under the hood.
We'll look at some of the equations. Not today, though, because it's a lot. All right. Any other questions, guys? But you can start. This is the XOR problem, which we will do. As I said, a line cannot separate this, but a neural network can because it'll do something like this.
And it's not linearly separable, so you can't use perceptron, right?
That's right, exactly. So that's the whole point of that second exercise. That's called the XOR problem, and we can only do it with neural nets.
You can't use K to your snapper.
Exactly. K and N may not be sufficient. You're right. Yeah. Yeah, that's where we're going. Okay. All right. So I'm trying to advance here. So let's go ahead. But I probably won't be able to finish. All right. So anyway, let's stick with this. I want you to nail this, because if you understand this, you'll be able to develop these. So definitely ask questions. But there's only a few elements that you need. You need these linear things, nn.linear and n.linear. What were these? I already described what these were. If you remember, this was y equal wx plus b. Do you remember that? that I gave you that example. You give it X, you learn W and B and produce Y. Remember that? Well, that equation, the line equation, is linear. Only PyTorch created linear to make it easy for us, but we should never forget that inside it is Y equal WX plus B. Okay? Go back to that previous video that we did last Tuesday. I covered all of that. All right. So anyway, so this allows us to create the little segments of the neural network from one layer to the next. And that's why they're deep, right? So then you add another linear and they just start to get really deep. But in between them, you need to add these activation functions such as sigmoid. And notice here we have another one called a softmax at the very end. We use this one for classification. It's similar to the sigmoid function with the additional step that the values need to add up to 1. I'll show you this later, okay? There's an equation for that as well. Just trust me for now. This is important to achieve better results. But it's similar to the idea of sigmoid, right? So what comes out of this function, which is of size 3, still needs to be run through a function called a softmax in this case, okay? Questions? All right, so that's it basically. So you can see then now we want to enable the activate, oops, the next, and I want to enable this. So effectively, this is really the thing that should guide you. You give the neural network X, it starts here. If X is 4, this needs to be 4. Then it comes out here to this X. After a linear function in a neural net, you need to run it through an activation function, such as ReLU or sigmoid or tan8. There's a whole bunch of them. So it goes in here, and that gets changed again to become this X. Now you want to run it through the output layer from the hidden layer. So that means that this X goes into, notice this was linear 1. Now this is linear 2. Okay. What you get here in this X is really that final thing with 3 neurons, but you still want to run it through an activation function. Okay, by definition, a neural network at the universal function approximator needs to have, let's say, at least 2 layers, and those layers need to run through activations. Okay, just make a note of that for now. We're going to drill down into those ideas going forward. But that's it. That's a neural net. So from here, I can just keep adding layers and make it deep learning, right? So that I took out the dropout. Let's not even worry about that for now. Now notice that the last thing is once you predict Y pret, you just return it. That's it, right? Okay, so let me run this one. And now in contrast, I'm going to give you a deep neural network, and we're going to have to end it there. And then please remember the presentations are Thursday, for those of you that haven't presented. So if you notice, once this architecture is done, the next step is to do the train loop, and that's the training. We're almost done, right? So, but let's look at this one. This is another architecture. So what I love about this object-oriented approach is I can just take one out and put another one in. I can just like building blocks, I can exchange them easily. So go ahead now, let's copy this one and let's talk about it. So here I'm defining another class. Notice I added the comment here. This is deep learning with 2 hidden layers. Again, I'm going to take out these normalization things to avoid complication. I'm going to take these out, and I'm going to take this normalization thing, it's a standardization thing out. All right, so you can see that there. I'm going to take out the dropouts also, just, we don't need that for this one. So you can basically get rid of it. All right, so this is how I define a deep neural network. I can see right here, 4, 15, 9, 3. Okay, so let's draw this. Deep learning just basically means more than one hidden layer, basically. That's it. Jeffrey Hinton coined the term. It's just deep because it's got more. So our MLP the first one, look like this, right? 1, 2, 3, 4. 1, 2, 3, and we made it of size 5 because that's what we chose. That's the MLP. Deep learning with 2 hidden layers basically means what? It's still iris data, right? So the input is still 4. Do you guys agree with that? It's still 4. The output is still a vector of 3, but instead of 1 hidden layer, how many layers am I going to have now? 2. What were their dimensions? Do you remember? One was 9, right? Was it 9? Oh, 15 and 9, actually. So this 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's what that means. 1 layer with 15 neurons. And this one is 9, I think it was, right? Yep. So 1, 2, 3, 4, 5, 6, 7, 8, 9. What does that translate to? More connections. Do you see that? Now, see this one has 1. Just look at this neuron, right? So this one has 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, all the way to 15. That's more opportunities to learn, to be more powerful. Do you guys understand? Yeah. And now, instead of going directly to the output, I'm going to look at my data, transform it, and that newly transformed version of it will go to another layer. So it's like, here is one inspector that looked at the data and made a decision. But then here's an inspector, looked at the data, made a report, and gave that report to a second inspector that looked at that data and made a prediction. You see that? So that's kind of the intuition with deep neural networks.
Is that word propagation?
This is forward propagation. It's in this direction. We're gonna do that later also. We did that actually last Tuesday. I did forward propagation. But we'll come back to this, okay? So understand right now what's really important, and I know I'm a little over time. Understand the difference between MLP and DL. Do you guys see that? So they have different architectures, and let me just show you that this one now has, so whereas this one had linear 4 to 5 and linear 5 to 3, this one now has linear 4 to 15, linear 15 to 9, linear 9 to 3. And that captures that drawing that I just made. Yeah.
What the exams may have a little.
Yeah. I may not include this last part, okay? But yeah.
Essentially deep learning opportunities.
Yeah, more connections, yes. More ways to learn and look at things. Yeah. All right, so yeah, I know I'm out of time. This is really important because this is actually the whole thing. I'll finish this next Tuesday, I guess, because we have the presentations on Thursday. Okay. If you guys have any questions or want to see me during office hours, just send me an email. All right. Otherwise, have a good one, and I'll see you on Thursday.
I can show you the perception thing that they're up.
Yeah, later.
Like, I don't know, like, during office hours.
Yeah, not right now because I'm pretty tired. Yeah.
Error with my camera. Can I show it to you?
Sure.
Okay, I have all the CSVs. I feel like I'm almost there.
Sure.
Okay.
I cannot be here Thursday. I had a relative pass away, so I have a funeral Thursday.
Okay.
I can give you that, whatever you would need for that.
I just want you to present.
So my question was gonna be, can I present Tuesday, but
Oh,
the exam is Tuesday, so.
Oh, yeah, that's right. Oh, yeah, that's right. The exam is
That was-
Tuesday.
Wow, yeah.
Yeah. You need to present at some point.
No, I know that. I'm not saying I don't.
We'll
just-
find a time.
Okay. Do you need anything from me for this, for like the funeral in terms of like that?
No, no, I don't need that. I just need you to present. Yeah.
Okay.
Yeah.
It's on Thursday, right?
Yeah, if you can
Exam
present.
is Tuesday.
Yeah, the exam is Tuesday. Present this Thursday and the exam is a week from today. Huh?
We finish both. Serious,
Yeah,
the class is in my study for my semester.
okay, thank you.
So this is my label. I don't know if my label is a problem.
Yeah, probably. This is where usually students have had
That
issues.
is my label.
Yeah, yeah.
Am I not supposed to put like?
Oh, hold on, let me end this video thing.